Welcome students to the third lecture on determinants. In the last two lectures, we have defined what is a determinant for a square matrix, and also we have defined or we have seen several properties of a determinant. In this lecture, we shall compute the determinant of several matrices by using those properties, so that the original matrix gets simplified and computation of the determinant becomes easier. Consider example 1. Find the determinant of A is equal to 1 x square 1 x square 1. Of course, we can compute its determinant from the first principle, that is by expanding along one row or one column, but we shall exploit some properties of determinants so that we can make it simple. Since we know that by adding two rows we do not change the value of the determinant, so we will try to use that property here. Say for example, I change the row 1 as the summation of row 1 and row 2. Therefore, determinant of A is equal to the determinant of, by adding row 1 and row 2 we find 1 plus x square, x plus 1, x square plus x. Row 2 remains the same, row 3 also remains the same. Now, I can see that we have 1 plus x square, 1 plus x, x square plus x in the first row, but in the third row we have x square and we have 1. So, what happens if I replace the first row as the sum of first row and third row? Then determinant of A is equal to determinant of 1 plus x square. Now, adding this to this, 1 plus x square, and adding 1 to this, 1 plus x square. Other rows remain the same. Now, what we find that in the matrix all the elements of the first row are 1 plus x square. Therefore, determinant of A is equal to determinant of, say, 1 plus x square into determinant of 1 x square 1 x and x square 1. Now, we do very similar thing with respect to the columns. We replace column 1 by the difference of column 1 and column 2. So, we write column 1 is now C 1 minus C 2. Therefore, determinant of A is equal to 1 plus x square into, after subtraction I get 0 1 1 x square minus 1 1 x minus x square 1. Now, what we do? We subtract column 3 from column 2. After doing that, we find that determinant of A is equal to 1 plus x square into 0 x square minus 1 x into 1 minus x 0 1 minus x square minus 1 1 x 1. What is the advantage? The advantage is that now in the first row we have 2 zeros and only one non-zero element, which is 1. Therefore, if I now expand it along the row 1, I get that determinant of A is equal to 1 plus x square into determinant of 0 0 1 x square minus 1 1 minus x into 1 minus x square minus 1 into 1 is equal to 1 times this minus this, which is equal to x square minus 1 whole square minus x into 1 minus x whole square is equal to 1 plus x square. Now, I can take x minus 1 whole square common from both the terms. So, let me write it as then what is left here? We are left with x plus 1 whole square minus x is equal to 1 plus x square into x minus 1 whole square into this gives me x square plus x plus 1. Because the 2x term will come and 1x is subtracted from there. This is equal to x minus 1 into x square plus x plus 1 into another x minus 1 into x square plus x plus 1, which is equal to 1 minus x cube whole square. So, by doing the elementary row operations or column operations, where we are replacing one column by the difference between two columns or one row by the sum or difference of two rows, we simplified the whole thing to get the answer to be 1 minus x cube whole square. Okay, students. So, let me do a numeric problem. Find the determinant of root 11 plus root 3, root 20, root 5, root 15 plus root 22, root 25, root 10, 3 plus root 55, root 15, root 25. We know that if some row or sub column of a matrix, each element can be written as a sum of two quantities, then we can write the entire determinant of the sum of two determinants. Since we have the addition sign here, we can think that we can partition it into two parts, but we have to be little bit more careful, because root 11 is there and root 22 is there and root 55 is there. We can see both of them have the term root 11. So, we will be judicious in separating it. So, let me write it as determinant of A is equal to, first matrix is root 11, root 22, root 55, remaining things are same, root 20, root 25, root 15, root 5, root 10, root 25. Determinant of this plus determinant of root 3, root 15 and 3, which we write it as root 3 times root 3, root 20, root 25, root 15 and root 5, root 10 and root 25. Now, since all the elements have root 11 in this first one, I can take root 11 out and I get the determinant of a matrix. Similarly, all these have root 5 common, therefore, I can take root 5 out of it, and similarly all of these has root 5 common and I can take root 5 out of it. So, to simplify the notation, let me write it as determinant of A1 plus determinant of A2. Now, determinant of A1 is equal to, after taking out root 11, root 5, root 5, what we are left with is 1, root 2, root 5, 2, root 5, root 3 and 1, root 2, root 5. Now, looking at this matrix, since two columns are identical, we know that the determinant is going to be 0. Therefore, determinant of A1 is equal to 0. Therefore, we can write determinant of A is same as determinant of A2, which is equal to determinant of root 3, root 15, root 3 into root 3, root 20, root 25, root 15 and root 5, root 10 and root 25. Now, looking at this, we can see that we can take root 3 common out of the first column, root 5 we can take common from the second column, same is for column 3. Therefore, determinant of A is equal to root 3 into root 5 into root 5 into determinant of 1 root 5 root 3 2 root 5 root 3 and 1 root 2 root 5. So, let me compute its determinant. One into root 5 into root 5 minus root 6. So, 5 minus root 6 minus 2 into this product to this product, which is 5 minus root 6 plus 1 into root 15 minus root 15. This is equal to 0. So, we are left with minus 1 into 5 minus root 6 is equal to root 6 minus 5. Therefore, determinant of A is equal to 5 root 3 into root 6 minus 5. So, this is the answer of the overall determinant. Example 3, find the determinant of A minus B minus C 2A 2B B minus C minus A 2B 2C C minus A minus B. We need to compute the determinant. Now, we find that if we add the rows, what is going to happen? So, let me do two things at one go. R 1 goes to R 1 plus R 2 plus R 3. In the previous example, I have done it in two steps. First, row 2 was added to row 1 and then row 3 was added to row 1, but now let me do it at one go. So, what I am doing? I am adding these two rows to the first row. Then we get the determinant of A is equal to determinant of, as I add 2b and 2c, I get A plus B plus C. As I am adding B minus C minus A and 2c, I get B plus C plus A, and as I am adding 2b plus C minus A minus B, I am again getting A plus B plus C, and other rows remain as it is. So, this is the structure that I get. What is the advantage? The advantage is that I can now take A plus B plus C common from the first row. Therefore, determinant of A is equal to A plus B plus C into determinant of 1, 1, 1, 2b, b minus C minus A, 2b, 2c, 2c, C minus A minus B. Now, what I do? I will try to simplify it. How I will do that? I will subtract column 3 from column 1. Therefore, C1 is equal to C1 minus C3. After doing that operation, I get determinant of A is equal to A plus B plus C times 1 minus 1 is 0, 2b minus 2b is 0, and 2c minus C minus A plus B, whole thing will become A plus B plus C. Other columns remains the same. What is the advantage? The advantage is that now we can expand the determinant only taking this term and corresponding submatrix. I do not need to bother about what is happening with this and what is happening with this. Therefore, determinant of A is equal to A plus B plus C. Now, note that it is the third row first column. Therefore, minus 1 to the power 3 plus 1 into this A plus B plus C into the determinant of this matrix, which is 2b minus B minus C minus A, is equal to, this gives me 1 A plus B plus C, this gives me 1 A plus B plus C, and this will also give me another A plus B plus C, and the sign is positive. Therefore, the answer is A plus B plus C whole cube. So, that is the answer. Another example, find the determinant of x, x square, y z, y, y square, z x, and z, z square, x y. As we can see, if we do the row operations by adding or subtracting, we can get something. So, what we do? We do rho 1 is equal to rho 1 minus rho 2. Then determinant of A is same as determinant of what I am getting, x minus y. What I am getting here is x square minus y square, which is x minus y into x plus y, and what I am getting here is z into y minus x, and other rows remain the same. Now, we can see that we can take x minus y to be common from row 1. Therefore, determinant of A is equal to x minus y into determinant of 1 x plus y minus z, because the term there was y minus x, so a minus sign will come, y square zx z square xy. Now, in a similar way, now I will subtract row 3 from row 2. That means row 2 minus row 3 now goes to row 2. Therefore, determinant of A is equal to x minus y into determinant of 1 x plus y minus z, y minus z, y minus z into y plus z into x into z minus y, z square xy. Therefore, determinant of A is equal to, now I take y minus z from row 2 and we are left with 1 x plus y minus z, 1 y plus z minus x z square xy. Now, what we will do? We will subtract this row from this row. What will happen? It will make this 0 and it will make this minus x plus z. Therefore, again doing R2 is equal to R2 minus R1, we have determinant of A is equal to x minus y into y minus z into determinant of 1 x plus y minus z, 0 z minus x z minus x and z square xy. Now, from this row we can take z minus x common, is equal to x minus y into y minus z. If I take z minus x common, then what is left is 1 x plus y minus z, 0, 1, 1 z square xy. What is this determinant? So, let me first write it as x minus y into y minus z into z minus x into determinant of B, where this matrix is B. So, let us calculate determinant of B. So, if I expand along the first column, it is 1 into x y minus z square plus z into x plus y minus z is equal to x y minus z square plus x plus y plus z into z is equal to x y minus z square plus x z plus y z plus z square, and this cancels, is equal to x y plus y z plus z x. Therefore, determinant of A is equal to x minus y into y minus z into z minus x multiplied by x y plus y z plus z x. This is the answer. Another problem. What is the determinant of a square plus 1 ab ac ab b square plus 1 bc ca cb c square plus 1? This is a very tricky problem, because we cannot take anything common from any row, neither from any column. So, we do some trick. What we do? We multiply this first row by A, and to take care of that, I divide it by 1 by A, so that the determinant does not change. Similarly, I multiply the second row with B and divide it by B, and I multiply the third row with C and then again divide it by C, there, so that determinant does not change. Therefore, determinant of A is equal to 1 upon A B C into determinant of A into A square plus 1, A square B, A square C, second row by multiplying with B, and third row multiplying with C, we get what is the advantage? The advantage is that now we can take A common from the first column, B common from the second column, and C common from the third column. Therefore, determinant of A is equal to A B C divided by this A B C. Now, after taking A common out of the first column, we get this, B out of the second column, we get this, and C taken out of the third column, we get thus we are in a slightly better position, because ABC and ABC gets cancelled. Therefore, determinant of A is same as determinant of A square plus 1 A square B square to B square plus 1 B square C square plus 1. Still, we find that none of the rows we can break up as sum of 2, none of the columns we can break up as sum of 2 elements. So, we cannot simplify it in that way. So, what we will do, I will rather add row 2 and row 3 with row 1. Therefore, R 1 is equal to R 2 plus R 3 plus R 1 will give us determinant of A is equal to A square plus B square plus C square plus 1. Here we will get A square plus B square plus C square plus 1, and here also we will get the same thing. Other rows remain the same. What is the advantage? The advantage is that now we can take A square plus B square plus C square plus 1 common of the first row. Therefore, determinant of A is equal to A square plus B square plus C square plus 1 into determinant of 1 1 1 B square plus 1 B square C square plus 1. Now, let us subtract column 3 from column 1 and also column 3 for column 2. So, we are doing 2 at the same time. C 1 goes to C 1 minus C 3 and C 2 goes to C 2 minus C 3. Therefore, after doing these two operations, we get determinant of A is equal to A square plus B square plus C square plus 1 into determinant of. Now, this I am subtracting from this, therefore, 0, B square minus B square is 0, C square minus C square plus 1 is equal to minus 1. Now, I am subtracting this column from this column, therefore, it is 0, 1, minus 1, and we are left with 1 B square into C square plus 1. This makes our life very simple, because the entire first row is 0 except the 1 3 element. Therefore, use determinant can be obtained by computing this determinant, which is very simple, which is 1. Therefore, this determinant is equal to 1. Therefore, determinant of A is equal to 1 plus A square plus B square plus C square. That is the answer. Now, let me do an interesting problem. Find the determinant of A is equal to n, npn, ncn, n plus 1, n plus 1 p, n plus 1, n plus 1, c n plus 1 and n plus 2, n plus 2, p n plus 2, n plus 2, c n plus 2. Looks formidable, but we know how to make it simple, because we know that n p n is equal to factorial n for all n and n c n is equal to 1 for all n. Therefore, the A matrix will look simpler if I write it as n, n plus 1, n plus 2, n factorial, n plus 1 factorial, n plus 2 factorial and 1, 1, 1. Can we take anything common? If we look at the second column, we see that n factorial is there in all of them. Therefore, we can take n factorial out of the second column, and therefore, determinant of A is equal to n factorial times the determinant of n, n plus 1, n plus 2. After taking out n factorial from n factorial, we get 1. After taking out n factorial from n plus 1 factorial, we get n plus 1, and after taking out n factorial from n plus 2 factorial, we get n plus 1 into n plus 2, and of course, the third column remains same, which is 1, 1, 1. Now, what we do? We subtract second row from the third row. Therefore, R 3 is equal to R 3 minus R 2 makes that determinant of A is equal to n factorial into n 1 1, n plus 1, n plus 1 1. Now, as I am subtracting second row from the third row, I get 1. I get n plus 1 into n plus 2 minus 1, that is n plus 1 whole square into 1. Now, we simplify it further. As I subtract 1 from 1, we get 0. Now, we simplify it further. What we do? We subtract row 1 from row 2. Therefore, replacing row 2 is equal to row 2 minus row 1, we get determinant of A is equal to n factorial into n 1 1, 1 n 0, 1 n plus 1 whole square 0. Therefore, now if we expand along the third column, we have only 1 1, rest are 0. Therefore, determinant of A is equal to n factorial into minus 1 to the power 1 plus 3 into n plus 1 whole square minus n is equal to n factorial into n square plus n plus 1. So, let us verify it for a simple n. Suppose we want to verify for n is equal to 2, therefore, we know that A is equal to 2 factorial to 1, 3 factorial 3, 1, 4 factorial 4, 1. Therefore, determinant of A is equal to determinant of 2, 2, 1, 3, 6, 1, 4, 24, 1. Or determinant of A is equal to 2, 2, 1, 3, 6, 1, 1, 18, 0. This we get by making R 3 is equal to R 3 minus R 2 is equal to determinant of 2, 2, 1, 1, 4, 0, 1, 18, 0, and this we get by making R 2 is equal to R 2 minus R 1 is equal to, now if I expand along this third column, we get only determinant of A is equal to 1 into 18 minus 4 is equal to 14. Now, if you remember, we got for general n determinant of A is equal to factorial 4 into n square plus n plus 1, putting n is equal to 2, we have n factorial into n square plus n plus 1 is equal to 2 factorial into 2 square plus 2 plus 1 is equal to 2 into 4 plus 2 plus 1 is equal to 2 into 7 is equal to 14. Therefore, we verify the answer with n is equal to 2. Therefore, that gives us the determinant of the apparently complicated matrix with the permutation of n and combination of n formula inside. Okay, friends, with that I stop here today. In this class, we have solved several problems which I believe will make you understand how to deal with the problem of computing determinants by first executing some appropriate row and column operations, which will make the computation of the determinants, simple. In the next classes, I shall look at some properties of determinant with respect to computation of area of a triangle, and also I will be talking about minors, cofactors, adjoint matrix, etc., with respect to the determinants of square matrices. Okay, students, thank you so much.